Hi everyone, I'm Roy. In this lesson, we'll follow the EWRB Electrical Inspector Teaching Guidelines 2021 Theory section, covering all written exam topics, from responsibilities of an electrical inspector, inspection requirements and legislation, to protective devices, cabling, testing and professional knowledge. Let's get started now. Hi, I'm Roy. This series is your guide to the NZ Electrical Inspector Theory exam. We'll cover each subtopic in EWRB Teaching Guidelines for Electrical Inspector, program outline for examination step by step, from inspection limits to testing, MEN systems, and legal duties. This guideline is available as a free download from the EWRB website. Each video gives a clear explanation, followed by Moodle-style quiz questions to help you pass with confidence. Here's a quick breakdown of Section 10.1.1, Limits of Work for Electrical Inspectors. First, inspectors can carry out all prescribed electrical work listed in Schedule 1 of the ESR, unless restricted by the board under Section 103 of the Electricity Act. Second, inspectors must not inspect work they did themselves, supervised, or issued the Certificate of Compliance for. That's straight from ESR 71.2 to prevent any conflict of interest. Third, inspectors must not inspect high-risk work unless they are competent, as defined in AS/NZS 3000. Know your limits. It's not just about what you can do, but also what you shouldn't. Let's test your knowledge next. Check out the Moodle questions. Each question will only stay on screen for a few seconds. Pause the video to answer, then resume when you're ready. The correct answers are in the description below. Stay sharp and good luck. Hi everyone, I'm Roy. In this lesson, we're looking at 10.1.2 Inspection Requirements. Let's go over what inspectors must check and when inspection is needed. Inspection ensures the installation is safe and meets regulatory requirements. Under ESR 60, not all prescribed electrical work needs inspection, but for high-risk work, like mains, medical or hazardous areas, an independent inspection is mandatory. You can't just rely on the COC. Section 82 of the Electricity Act lets you connect the supply temporarily for testing and inspection. This helps confirm safety before you issue full certification. Inspectors must confirm that the person who issued the COC is authorized. You can check their current license using the public register. All work must meet AS/NZS 3000 and other cited standards, inspection or not. Compliance is always required. Even if low or extra low voltage work doesn't need inspection, it still must be safe, tested, and comply with AS/NZS 3000. If the job was done to a certified design, the inspector must ensure the completed work exactly matches that design and complies. Great work so far. Now we'll go through some Moodle-style questions to reinforce the key points from 10.1.2 Inspection Requirements. These questions are designed just like what you'll see in the real exam. Let's get into it. Hi everyone, I'm Roy. This short lesson covers 10.1.3, Inspection Work Safety and Offences. We'll look at the inspector's safety responsibilities and the legal consequences of doing unsafe or non-compliant inspections. Let's begin. All inspection work focuses on safety, protecting people, livestock, property, and equipment. That includes checking for shock risks, overheating, and correct installation of fittings and appliances. If an inspector signs off electrical work that's not compliant with the regulations, they may commit a Level 2 offence under ESR 73. This includes failing to meet inspection duties or verifying safety. Under Sections 163C and 163D of the Act, inspectors or anyone doing unsafe electrical work can face serious penalties, including large fines or even prison, if their actions cause serious harm or damage. Now, let's go through some Moodle-style questions to check your understanding of what inspectors must do to keep people safe and what the law says when things go wrong. Hi everyone, I'm Whitroy. In this short lesson, we're looking at 10.1.4, Documentation General. As inspectors, we must understand the purpose and correct use of key documents like ROI, COC, and ESC. Let's take a look. Documentation isn't just paperwork, it's a compliance requirement. ESR 73A states inspectors must evaluate the purpose and correct format of safety, testing, or design documents used for electrical certification and inspection. If the person connecting the installation didn't do the testing, they must cite signed documentation stating what was tested and the results. ESR 73A4 allows you to rely on existing COCs, but only if you act in good faith and reasonably trust their accuracy. ROI, COC, and ESC are essential documents. As inspectors, we must ensure they are properly completed and reflect the actual work and safety verification done. Supporting documents include WOEFs for mobile setups, certified designs, and periodic certificates for older or temporary installations. Inspectors must also understand test tagging under AS NZS 3760. That wraps up our short lesson on documentation. Now let's go through some Moodle-style questions to test your understanding of the key forms when they're required and what ESR 73A expects of us as inspectors. Hi everyone, I'm Whitroy. In this short lesson we'll cover 10.1.5 ethics. We'll look at the professional responsibilities and ethical expectations for electrical inspectors, including reporting duties, accountability, and providing industry support. Inspectors must report any immediate danger to life or property they find while carrying out PEU. This must be reported without delay to the site owner and to WorkSafe. The high-risk database can be audited by WorkSafe. Inspectors must ensure their entries are accurate and submitted on time, as incorrect records may result in legal action. If an inspector is found guilty of a disciplinary offence after an investigation, the board may take action, including suspending or cancelling their registration. Inspectors are often looked to for advice. If you're offering mentoring or support, be sure your knowledge is current and reliable, so you're helping promote electrical safety across the industry. That wraps up our quick look at ethics and responsibilities. Now let's go through some Moodle-style questions to check your understanding of safety duties, reporting obligations, and professional conduct as an inspector. Hi everyone, I'm Whitroy. In this lesson we'll look at 10.1.6.1 Record of Inspection. We'll cover what an ROI is, when it's required, and what inspectors must do to meet their legal obligations. An ROI is a legal document confirming that an inspector has verified high-risk prescribed work. It must be prepared in writing and kept for at least 7 years, either on paper or electronically. The inspector must give a copy of the ROI to the person who arranged the work, either the electrical worker or the site owner, within 20 working days of issue. Inspectors must upload the ROI to WorkSafe's high-risk database. It must include details like the COC and be submitted in the correct format within 20 working days. To upload an ROI, inspectors must register with WorkSafe and use the HRDB system. This ensures only authorized people submit or access inspection records. The HRDB is open to the public. This means owners or agents can check whether inspection records exist for their installation, supporting better safety compliance. That's the end of our short lesson on records of inspection. Now let's go through some Moodle-style questions to help reinforce when an ROI is required, how it must be handled, and what your responsibilities are as an inspector. Hi everyone, I'm Whitroy. In this lesson, we'll cover 10.1 6.2 certificates of compliance and electrical safety certificates. These are the key documents that prove prescribed electrical work is safe and lawful. Let's go through what they are, who issues them, and what must be included. Different trades may complete different parts of an installation. Each one must issue their own SAHI or ESC covering only their work. A certificate of compliance must be issued for all general and high-risk prescribed electrical work. Without it, the job is not legally complete. An electrical safety certificate must be issued when prescribed electrical work leads to connection or reconnection of an installation or fitting. It proves that the installation is safe and complies with regulations. An electrical safety certificate must be issued when prescribed electrical work results in an installation being connected or reconnected to power. The COC covers the quality and compliance of the electrical work itself. The ESC confirms the whole installation is safe to connect to power. If the job involves energizing, both documents are usually required. If a COC has incorrect or missing information or lacks backup like test results, an inspector must not accept or rely on it. A COC confirms that the work meets safety and legal standards. It must be based on proper testing and verification. A valid COC must record who did the work, what was done, and when. It must be signed by the person responsible. Issuing a COC with false or misleading details is an offense. It can lead to prosecution and serious consequences. The law requires that these certificates be kept for at least 7 years after the job. They must be made available during audits or investigations. That's a wrap on our lesson about COCs and ESCs. Now let's go through some Moodle-style questions to check your understanding of who issues these certificates, when they're required, and how they must be managed under the regulations. Hi everyone, I'm Whit Roy. In this lesson we're looking at 10.1 6.3 Certificate of Periodic Verification. You'll learn when this certificate is required and who is authorized to issue it. If an electrical installation has been disconnected for more than 6 months, it cannot be reconnected without a certificate of periodic verification. This must follow AS NZS 3019 and be signed by someone qualified to certify mains work. That finishes our quick overview of periodic verification. Now let's go through some Moodle-style questions to check your understanding of when this certificate is needed and who can issue it. Hi everyone, I'm Whit Roy. This lesson covers 10.1 6.4 Warrant of Electrical Fitness or WOEF. We'll look at when it's needed, who can issue one, and what must be included. Let's begin. A WOEF is a legal document confirming a connectable installation in a vehicle, relocatable building, or pleasure vessel is safe to use. It includes a form, test records, and a sticker applied to the installation. Before connecting any power to a connectable installation, the person supplying electricity must confirm that a current WOEF is in place. This ensures the installation is safe before it's energized. A WOEF can only be issued by someone authorized to inspect mains work, someone previously approved by the secretary for the same class, or the person who issued the COC under Regulation 66, but only if they issue it at the same time. A licensed electrician cannot issue a WOEF unless they meet one of these conditions. The WOEF must be completed using the correct form, affixed visibly to the installation, and copies must be kept and provided as required. A WOEF usually lasts 4 years, but for mobile medical facilities it's only valid for 1 year. Issuing a WOEF when you're not authorized or for an unsafe installation is a level 1 offense and could result in prosecution. That's the end of our lesson on 10.1 6.4 Warrant of Electrical Fitness. Now let's go through some Moodle-style questions to check your understanding of when a WOEF is required, who can issue it, and what the regulations expect from the person completing it. Hi everyone, I'm Whitroy. In this short lesson, we're looking at 10.1.7 periodic assessments of certain installations. We'll cover which installations require periodic safety assessments, who can carry them out, and what documentation is required under ESR 75. Let's begin. ESR 75 requires that specific types of installations, like caravan parks, boat marinas, and fairgrounds, are periodically assessed for electrical safety. These assessments must follow the timeframes and standards listed in ESR 75. 1. Not everyone can carry out these assessments. ESR 75 divides them by location. Some must be done by someone authorized for that installation, others by a person with specific competencies referred to in the standard. Once the assessment is done, a record of assessment must be completed, not a certificate. The form must say what standard or certified design was used, and it must be given to the requester and stored for at least 3 years or sent to WorkSafe. Failing to follow the requirements of ESR 75 can result in level 1 or level 2 offences, depending on whether you're the owner, the assessor, or knowingly using a non-compliant installation. That's the end of our short lesson on 10.1.7 periodic assessments. Now let's go through some Moodle-style questions to test your understanding of what types of installations need assessment, who can carry them out, and what documentation is required. Hi everyone, I'm Whitroy. In this short lesson, we're looking at 10.2.1, work requiring inspection. We'll identify what types of prescribed electrical work, PEW, require inspection, who can inspect it, and under what conditions. Let quote S dive in. Prescribed electrical work is classified into 3 levels of risk. According to ESR 6A, only high-risk PEW must be inspected. ESR 70 adds that the inspection must independently verify electrical safety, not just trust the COC. ESR 57 and 79 state that homeowners can carry out some types of PEW, but not high-risk work. Any PEW they do must still be inspected and certified by a licensed professional before connection. Mains work is usually high-risk prescribed electrical work and requires inspection, but under ESR 4, some exceptions apply, like revenue meter installation, as long as it does not affect the integrity of the neutral or transpose active and neutral conductors. Similarly, replacing the MEN link for testing may also be exempt. An inspector may only inspect PEW if they are competent and authorized for that type of work. This ensures the inspection is valid, safe, and compliant. That wraps up our short overview of 10.2.1 work requiring inspection. Now let's review some Moodle-style questions to check your understanding of what work must be inspected, who can inspect it, and how to apply the rules in practice. Hi everyone, I'm Whitroy. In this short lesson, we're covering 10.2.2 low voltage electrical installations. We'll look at the legal and standard-based requirements for installing, inspecting, testing, and verifying low voltage systems, especially those using the MEN system. According to ESR 59, low voltage electrical installations must comply with AS/NZS 3000. Part 2 generally applies to standard domestic installations, while Part 1 is more flexible for alternative design approaches. ESR 63 requires testing of all PEW done on low voltage installations. That testing must follow the methods in AS/NZS 3000 such as insulation resistance, polarity, and earth continuity. Even if a COC has been issued, the inspector must carry out their own checks. AS/NZS 3000 Section 8 explains what verification tests are required, including inspection of the main earthing system, switchboard wiring, and MEN link. Some electrical work falls under other standards in addition to AS/NZS 3000. ESR 60, 1, ensures that if another cited standard applies, it must also be followed, like AS/NZS 60,000 and 79.17 for hazardous areas. According to ESR 27, every standard low voltage installation must use a multiple earth neutral MEN system. At least one MEN switchboard is required, and it must be the one electrically closest to the point of supply. That wraps up our short lesson on 10.2.2 low voltage electrical installations. Now let's go through some Moodle style questions to test what you've learned, including MEN rules, verification testing, and the application of AS/NZS 3000. Hi everyone, I'm Whit Roy. In this short lesson we're covering 10.2.3 high voltage installations. We'll go through the key certification and inspection requirements and the risks that come with testing and working on high voltage systems, all align with the electricity safety regulations and NZECP 34. According to ESR 58 and 62, high voltage work must be based on a certified design. That design guides the installation, testing, and connection and must be available on site. Under ESR 72, any prescribed electrical work on high voltage installations must be certified and inspected. This applies to all voltages above 1000 VAC or 1500 VDC. When inspecting high voltage installations, you must verify compliance with both NZECP 34 and key high voltage regulations, ESRs 34 and 41 through 44, to ensure work is done safely and meets legal requirements. Testing and inspecting high voltage systems requires strong theoretical understanding. You must know how step and touch voltages pose danger and follow the clearance and earthing rules outlined in ESRs 13 to 17 and NZECP 34. That's the end of our short lesson on 10.2.3 high voltage installations. Let's now review some Moodle style questions to reinforce your understanding of certification, safety, and regulation compliance in high voltage environments. Hi everyone, I'm Whit Roy. In this short lesson we're focusing on 10.2.4 medical locations. Medical areas, particularly those involving patient treatment, require specific electrical safety considerations. We'll explore patient zones, shock hazards, key standards, and compliance checks, especially for mobile medical setups. A medical location refers to any place where electrical equipment is used for patient treatment. This includes hospitals, dental rooms, and mobile medical units. According to ESR Schedule 4, medical locations include both patient treatment areas and mobile medical facilities. AS/NZS 2500 explains two main electrical risks, microshock and macroshock. Microshock is especially dangerous in cardiac areas where currents as small as 100 microamperes may cause fibrillation. That's why equipotential bonding is so critical in cardiac protected zones compared to general body protected zones. Installations in medical locations must comply with standards like AS/NZS 3003 for patient zones and NZS 6115 for mobile units. Any LV work in these areas is prescribed, meaning it must be done by a licensed person. A warrant of electrical fitness, WOEF, must be issued annually by an authorized inspector according to ESR 78-2B. In this lesson, we've covered the electrical safety requirements for medical locations, including patient zones, microshock hazards, and the need for equipotential bonding. We also looked at the compliance rules from AS/NZS 2500, AS/NZS 3003, and NZS 6115. Let's now go through some Moodle questions to reinforce these critical inspection principles. Hi everyone, I'm Whit Roy. In this short lesson, we're looking at 10.2.5 hazardous areas. This topic is critical because hazardous areas can involve explosive atmospheres. So electrical work here must follow strict safety rules under ESR and AS/NZS standards. A hazardous area is any location where flammable gases, vapors, or combustible dust may be present in quantities that could ignite. According to ESR, even work involving extra low voltage is still considered prescribed electrical work if it's in a hazardous area. That's because any spark could cause serious danger. Installations in hazardous areas must be designed and initially inspected according to AS/NZS 60079.14, which includes selecting and erecting equipment based on gas classification and zone. For ongoing maintenance and testing, AS/NZS 60000 and 79.17 applies. These standards are referenced in ESR Schedule 2, making compliance mandatory. When inspecting or maintaining installations in hazardous areas, you must follow the relevant standards and create a record of assessment as required under ESR 75(1)(e). This includes stating which standard was followed and under ESR 75(4), keeping a copy for at least 3 years, or sending it to WorkSafe. AS/NZS 60000 and 79.14 highlights that hazardous areas contain flammable gases or vapors that can ignite. Inspectors must ensure equipment used does not become an ignition source. Applying correct installation techniques and selecting certified equipment reduces the risk of fire or explosion. We've now explored how electrical work in hazardous areas is defined, installed, inspected, and maintained under ESR and AS/NZS 60079. Next, we'll go through some Moodle questions to reinforce your understanding, especially around standards, inspection responsibilities, and documentation. Hi everyone, I'm Whitroy. In this short lesson, we're focusing on 10.2.6 animal stunning and meat conditioning appliances. This is a special category of high-risk prescribed electrical work that involves serious safety risks. Let's break down what the standards require. Any electrical work done on animal stunning or meat conditioning equipment is considered high-risk prescribed electrical work. That means it must be certified and independently inspected according to ESR 6A. When doing this kind of work, testing must be done to NZS 6116, and installation must meet the performance requirements of AS/NZS 3000 Part 2. This is a legal requirement under ESR 62B. According to NZS 6116 2006 Clause 4.4.2, all plant and equipment, including animal stunning gear, must be inspected before use and safely isolated during any checks or servicing. These devices may involve high voltage and operate in wet or harsh environments. Inspectors must control the risks of shock, mechanical damage, or accidental activation by following strict isolation and inspection procedures. That wraps up our lesson on 10.2.6 animal stunning and meat conditioning appliances. These are serious pieces of equipment and the regulations treat them accordingly. Let's go through some Moodle-style questions to test your understanding. Hi everyone, I'm Whitroy. In this short lesson, we're going to look at mains parallel generation systems. These are systems like solar or backup generators that connect to the national grid. We'll focus on what the regulations require before connection, during testing, and for emergency supply systems in hospitals. These systems carry specific dangers like backfeed and shock risk during maintenance. That's why inspection procedures must be followed carefully, especially where connection to the grid could pose danger to workers or the public. Before a mains parallel generation system is connected to supply, ESR 73AE requires it to be tested and verified as electrically safe. This includes carrying out all required checks to ensure compliance and safety before energizing the system. When doing this kind of work, testing must be done to NZS 6116 and installation must meet the performance requirements of AS/NZS 3000 Part 2. This is a legal requirement under ESR 62B. When backup power is installed in a hospital, ESR 62E requires that the emergency supply system complies with AS/NZS 3000 and AS/NZS 3009. These ensure life-saving equipment remains powered even during a fault or outage. Now that we've looked at the certification, testing, and emergency backup rules for mains parallel generation systems, let's go through some Moodle questions to help reinforce your understanding of ESR 60, 70, 73A and how AS/NZS standards apply. Hi everyone, I'm Whitroy. In this lesson, we're focusing on photovoltaic systems, commonly known as solar installations. We'll look at why these systems are treated as high-risk PW under the regulations and the exact standards they must comply with under the electricity safety regulations. According to ESR 6A and Schedule 1, any photovoltaic PV system installed in an installation is prescribed as high-risk prescribed electrical work. This means it must be certified and inspected, no exceptions. Even the low-voltage DC component of a photovoltaic system is considered high-risk PW under Schedule 1. This means installers and inspectors must treat it with the same seriousness as the AC side. When your PV system includes an inverter that connects to the national grid, it becomes a mains parallel generation system. Under ESR 62F, it must comply with AS-NZS 3000 and AS-NZS 4777.1, which includes detailed safety and design requirements. ESR 62D says that when you install a photovoltaic system under Part 2 of AS-NZS 3000, it must also comply with AS-NZS 5033. This standard covers specific PV safety and installation conditions such as string configurations, labeling, and disconnection devices. Photovoltaic systems are common, but they carry serious risks and obligations under ESR. Knowing when certification is required, which parts are high risk, and what standards apply is essential. Let's now go through some Moodle questions to reinforce your understanding of ESR 6A, 60, and Schedule 1. Hi everyone, I'm Roy. In this lesson, we're going to explore installations that do not comply with Part 2 of AS-NZS 3000. We'll look at what certified design means, the safety rules under Part 1, and when these provisions apply under the ESR. AS-NZS 3000 consists of two parts. Part 2 provides the methods and practices that are deemed to comply. Part 1 outlines the fundamental safety principles and design objectives that apply to all installations. Under ESR 59.2, low voltage or ELV installations may be constructed using a certified design. This design must comply with Part 1 of AS-NZS 3000 and clearly document why a departure from Part 2 is necessary. A certified design under ESR 58.1 must specify the location of the installation, identify the standards it follows, and include the designer's name, signature, and date. This ensures traceability and accountability. An installation built to a certified design must still be tested and inspected. According to ESR 58.2, this inspection ensures the installation is electrically safe and meets the intent of the certified design. When Part 2 of AS-NZS 3000 can't be followed, a certified design becomes a vital tool. But it brings strict documentation and inspection requirements under the ESR. Let's now go through some Moodle questions to reinforce your understanding of ESR 58, 59, and AS-NZS 3000. Hi everyone, I'm Roy. In this short lesson, we'll look at switchboards, including MEN switchboards and the requirements under the Electricity Safety Regulations and AS-NZS 3000. We'll cover key components, testing, location requirements, and earthing arrangements. A switchboard is where electrical circuits are controlled and protected. Under AS-NZS 3000 Section 1, an MEN switchboard is part of the earthing system, ensuring safety through neutral connections to earth. It's important to know the role of each component, switchgear, distribution boards, and main boards, in a complete installation. Before energizing, switchboards must be tested to confirm safety and compliance. ESR 61 requires this testing to meet the standards in AS-NZS 3000. Key tests include earth continuity, insulation resistance, and verifying MEN connections. AS-NZS 3000 sets out specific site and construction rules. For example, Clause 2.9 requires protection from fire spread, while meter access must be maintained under energy supply rules. Switchboards must also be clearly labeled and accessible for maintenance. The MEN, Multiple Earth to Neutral System, is the standard earthing system in New Zealand. According to Section 5 of AS-NZS 3000, the neutral conductor must be earthed at the main switchboard. This helps ensure that fault currents return to the supply source and protective devices operate correctly. In this lesson, we've covered the role of MEN switchboards, required testing, installation rules, and earthing under AS-NZS 3000 and the ESR. Let's now go through some Moodle questions to reinforce these key inspection concepts. Hi everyone, I'm Roy. In this short lesson, we're going to look at employer licenses, what they are, how they work under the Electricity Act and ESR, and how they affect certification when work is done by unregistered employees. An employer license authorizes a person to carry out prescribed electrical work, PEW, even if they're not personally registered, as long as they're working under a licensed employer's system of operation. This is defined in sections 115 and 117 of the Electricity Act 1992. When someone working under an employer license certifies PEW, the documentation, like a COC or ROI, must include the employer license number instead of the worker's individual registration number, as stated in ESR 67(2)(d). When inspecting high-risk work carried out under an employer license, ensure that the license number is shown on certification and can be confirmed in the EWRB public register. This helps maintain safety and compliance transparency. Under ESR 94, license holders must run a formal system of operation to make sure employees doing PEW are trained, competent, and safe. The system must include procedures for work control, safety assurance, and quality. In this lesson, we explored how employer licenses enable certain workers to carry out PEW as long as they are competent and properly supervised and trained. Next, we'll go through Moodle questions to practice applying these compliance requirements in real situations. Hi everyone, I'm Whitroy. In this short lesson, we're exploring periodic safety assessments, what they are, their importance, and how to correctly conduct these assessments for various electrical installations. According to ESR 75(1), certain types of installations must undergo regular safety assessments. These include caravan parks, boat marinas, construction and demolition sites, carnivals and fairgrounds, hazardous areas, and medical facilities. The aim is to ensure all remain electrically safe and compliant.
The person completing the assessment must record if it followed a standard or certified design, name each one, give the record to the requester, and keep or send a copy to WorkSafe. If a standard prescribes a form, it must be used.
Different standards apply depending on the installation type. For example, caravan parks follow AS/NZS 3001, boat marinas use AS/NZS 3004.1, and construction sites adhere to AS/NZS 3012. Specialized environments like carnivals, hazardous areas, and medical locations each have their specific safety standards to follow. Who can do the assessment depends on the installation type. For caravan parks, boat marinas, and construction sites, only someone authorized to assess prescribed electrical work can do it. For hazardous areas, carnivals, or medical setups, the person must meet the competencies stated in the relevant standard. Great work. That's our overview of 10.3.1 on periodic safety assessments. Next, tackle some Moodle questions to test your understanding of when and how to perform these essential assessments accurately. Hi everyone, I'm Whitroy. Today we'll look at connectable installations, what they include, testing and safety verification, and the conditions for use. The Electricity Act defines a connectable installation as an installation in a vehicle, relocatable building, or pleasure vessel designed or capable of connecting to an external power supply at or above the voltage prescribed by regulation. It also includes all electrical appliances connected to it.
Under ESR 78, a new connectable installation must be tested before it can be connected to a power supply. The testing must follow Section 8 of AS/NZS 3000. No connection is allowed unless the installation is confirmed to be electrically safe.
Different types of connectable installations have specific safety standards. Pleasure vessels follow AS/NZS 3004.2. Mobile medical facilities use NZS 6115, and most others follow AS/NZS 3001. Imported connectable installations must comply with AS/NZS 3001 and also be assessed under Part 1 of AS/NZS 3000.
Before supplying electricity or leasing out a connectable installation, you must check that it has a current warrant of electrical fitness, UOEF. ESR 76 and 77 make this mandatory.
Great job. That's a quick look at connectable installations under 10.3.2. Now try some Moodle questions to ensure you're clear on verifying, testing, and using these installations safely. Hi everyone, I'm Whit Roy. Today we'll explore the critical steps needed to verify electrical safety before connecting installations to a power supply. Before connecting low voltage installations, check that polarity and phase rotation are correct, protection is rated correctly, the system is compatible, and for MEN supplies, confirm there is a main earthing system.
If you didn't do the testing, you must check signed documents that show what was tested and the results.
Connection means the final piece of prescribed work that lets electricity flow, whether it's for the full or part installation. High voltage connections require strict compliance with ESR 73.2 and ESR 38.2. All mandatory safety checks must be confirmed before proceeding. Great job! That covers verifying safety for connecting installations. Let's now move to Moodle questions to reinforce our understanding and ensure safe connection practices. Hi everyone, I'm Whit Roy. Today we'll cover appliance and equipment safety, focusing on standards, risk categories, and compliance procedures essential for electrical safety. All electrical products sold in New Zealand must adhere to recognized safety standards as outlined in Schedule 4 of the ESR.
A registered ESS product is a medium or high-risk appliance tested and listed by a responsible supplier in the EESS database. This ensures regulatory compliance and traceability. Supplier declarations of conformity confirm compliance with regulations. Medium and high-risk articles need specific approvals to be legally sold.
Appliances are classified as safe or unsafe based on clearly defined ESR criteria, ensuring consistent safety standards.
If an appliance fails safety testing, ESR 92B requires it to be permanently disabled and clearly marked. This stops it from being reused and alerts others to the hazard.
New appliances must meet AS/NZS 3820 or ESR Schedule 4 standards. Used appliances require testing and tagging according to AS/NZS 5761.
Appliances must be tested after any safety impacting work, following AS/NZS 5762. Medical and hazardous area equipment also require specific compliance documentation.
Great job, we have covered appliance and equipment safety. Now test your knowledge with Moodle questions to reinforce these critical compliance and safety checks. Hi everyone, I'm Whit Roy. In this short lesson, we're looking at Electrical Workers Registration Board policies and rules. These policies outline how the board controls registration, supervision, and the responsibilities for trainees and licensed workers. Let's take a closer look. The Electrical Workers Registration Board, EWRB, has authority under Part 10 of the Electricity Act to set rules for registration, licensing, and competency. This applies to all classes of registration, including trainees and limited certificate holders. Each registration class has defined limits for performing prescribed electrical work, PEW. The EWRB publishes these limits in the Gazette, and they apply to every registration type, from electrical apprentices to inspectors. Supervisors are responsible for making sure supervised persons work safely and within scope. Both supervisor and supervised must understand their duties as outlined in the EWRB Supervision Policy and Companion Guide. Supervision itself is classified as prescribed electrical work under Schedule 1 of the Electricity Safety Regulations. Anyone supervising PEU must be registered and licensed appropriately.
There are specific exemptions under the Electricity Act for people working under supervision with a limited certificate, or those recognized as supervised persons even if they are not trainees. These exemptions are covered in Sections 76 to 78 of the Electricity Act 1992. A trainee can only assist with work that is within the class of registration they're pursuing. The work must also be something the supervisor is authorized to do. This is clearly stated under ESR 93.
That wraps up our overview of Electrical Workers Registration Board policies and rules. Now let's go through some Moodle questions to check your understanding of these supervision policies, limits, and responsibilities under the Act and ESR. Hi everyone, I'm Whit Roy. In this short lesson, we're going to cover 3 important areas for all electrical workers: practicing licenses, power of entry, and disciplinary offences. These are key parts of staying compliant and professional under the Act. Let's go through them. Just being registered doesn't mean you're allowed to carry out or assist with prescribed electrical work. Under Section 98, you also need a valid practicing license to be legally authorized to perform PEU. Section 83 allows authorized persons to enter a premises, including a home, to inspect or test prescribed electrical work, or to make inquiries to confirm if the work has been properly tested, certified, or inspected, but only with board authorization. Sections 142 and 143 cover who can be disciplined and what counts as an offence, like unsafe work using faulty fittings or breaching license rules. If a person is found guilty of a disciplinary offence, the board can act under Section 147M. Penalties may include suspending or cancelling registration, or limiting the type of electrical work the person can do. That wraps up our look at practicing licenses, entry rights, and disciplinary actions. Now let's go through some Moodle questions to check your understanding of these key responsibilities. Hi everyone, I'm Whit Roy. In this short lesson, we'll explore the safety competency requirements for persons carrying out prescribed electrical work. We'll also look at employer obligations and what happens when someone fails to meet competency requirements. Anyone doing PEW must take all practical steps to ensure the work is electrically safe and complies with regulations. This is clearly stated in ESR 100-1. Under ESR 100-1D, all electrical work on equipment operating at low or extra low voltage must comply with AS/NZS 4836 or the certified design. This ensures all safety requirements are met for such work. ESR rules are in addition to, not a replacement for, duties under the Health and Safety at Work Act 2015, as stated in ESR 100-2. Employers also have a duty under ESR 101 to ensure their employees are kept safe when carrying out electrical work. If someone is subject to disciplinary action, they may be required under Section 108, the Electricity Act 1992, to complete a competency program within a set time frame. The board requires people applying for, renewing, or holding a license to complete competency training. These rules are set out in Section 108 of the Electricity Act 1992. That's our overview of safety competency requirements under 10.4.5. Next, we'll go through some Moodle questions to reinforce what we've covered. Hi everyone, I'm Whit Roy. In this short lesson, we'll take a look at the Electricity Act 1992 and the Electricity Safety Regulations 2010 ESR, the 2 key legal documents that govern electrical safety and registration in New Zealand. The Electricity Act 1992 provides the core legislative authority for regulating electrical work. It outlines how safety, licensing, and enforcement are managed and is supported by the more detailed requirements in the ESR. Both the Act and the ESR are structured logically. Learn how to locate parts and sections quickly. Section 2 of the Act defines important terms like electrical installation, while ESR includes detailed rules across over 100 regulations. Get familiar with Regulation 3, Scope, Regulation 4, Interpretations, and Regulation 113, Non-Retrospective Safety. Learn how the schedules help you understand what work is PEU, what standards apply, and what is required for specific fields like mining. That's a wrap on 10.4.6. Now let's go through some Moodle questions to test your understanding of how the Act and ESR are structured and applied. Hi everyone, I'm Whit Roy. In this short lesson, we're focusing on standards and codes of practice, what they are, why we use them, and how to access the correct ones for your electrical work. You must follow the exact version of a standard cited in ESR, not necessarily the newest one. Registered people and limited certificate holders can access standards for free via the EWRB online portal. AS/NZS 3000 provides the foundation for most electrical installations. Part 1 gives general safety rules and Part 2 provides specific technical rules. AS/NZS 4836 is critical for safely working near or on live systems. Different standards apply depending on the installation type. For example, use AS/NZS 3012 for construction, AS/NZS 6115 for mobile medical installations, and AS/NZS 60079.14 for hazardous locations. That wraps up 10.4.7 on standards and codes of practice. Let's move on to some Moodle questions now and test your understanding of which standards apply in different scenarios and how to access them properly. Hi everyone, I'm Whit Roy. Today we're diving into the Multiple Earth Neutral (MEN) system. We'll cover its components, reasons for its use, and safety implications. The MEN system includes vital components such as earth electrodes, the MEN link, and neutral conductors. Multiple earth connections ensure safety by limiting voltage rise during faults and significantly reducing shock hazards.
The MEN link is crucial. It provides protection against electric shock and fires. Without it, installations can experience dangerous voltage levels, improper earth fault paths, and protective devices failing to operate correctly. MEN is popular due to reliability and simplicity. Alternative systems like TNS or TNC have separate earthing arrangements but involve more complexity. Each has its unique advantages and disadvantages.
Always check that the earth electrode is effective and that the neutral return path has the lowest impedance. If the neutral path has higher impedance than the earth path, current may flow through the earth instead. This can cause serious safety risks such as electric shock or fire.
AS/NZS 3000 Section 5 outlines strict earthing requirements for MEN installations. Adhering to these standards ensures installation safety and compliance, protecting people and equipment.
Great work, everyone. That covers MEN systems thoroughly. Next, let's apply this knowledge in some Moodle questions to reinforce your understanding. Hi everyone, I'm Whit Roy. In this lesson, we're discussing prospective short-circuit currents, understanding hazards, safety implications, and calculating these critical values. High prospective short-circuit currents pose serious hazards. They threaten personal safety, can destroy protective devices, fittings, and cause significant property damage. Recognizing these dangers is crucial for safe electrical installations.
Prospective short-circuit currents can cause intense electrical arcs, powerful magnetic forces, and mechanical failures. If equipment can't safely interrupt these currents, catastrophic damage and severe injury could occur. Selecting suitable protection devices such as MCBs, fuses, and circuit breakers involves ensuring they are rated for the expected short-circuit current and correct duty category. Proper selection ensures reliable operation, fault clearance, and the safety of the installation.
Accurate calculation of prospective short-circuit currents is essential for installations and individual circuits. This ensures equipment ratings are appropriate, preventing failures and promoting safety. A short circuit heats up conductors fast. We use a formula to work out how long the cable can handle that fault. It depends on the cable size, material, and insulation. The breaker must trip before it reaches the thermal limit. Let's work through an example using the short circuit thermal limit formula. Say we've got a 6 square millimeters copper cable, K is 111 and fault current is 3000 amps. Plug it into the formula, the result is about 0.49 seconds. That means the circuit breaker or fuse must trip in less than half a second to stop the cable from overheating. Great effort, everyone. Understanding prospective short circuit currents helps maintain electrical safety. Let's reinforce our learning with some Moodle questions next. Hi everyone, I'm Whit Roy. Today we're discussing reversed polarity, its dangers, testing methods, and the importance of correct phase rotation. Reverse polarity at the installation point can cause protective devices to fail, increasing the risk of electric shock and fire. Understanding these risks is crucial for electrical safety.
Before an installation is connected, polarity tests must positively identify the neutral conductor. Remember, testing must occur before energizing. Retrospective polarity testing isn't allowed. Safety verification methods are vital for identifying correct polarity even after connections are made. Consistent checking ensures installations remain safe over time.
Calculations help evaluate the risks of reversed polarity, explaining why protective devices might fail during phase-to-neutral transposition. Accurate assessments prevent hazards. In this example, a 50 kVA supply has a 60 amps fuse at the pillar and a 160 amps fuse at the transformer. With 230 volts and 12 ohms earth loop resistance, the fault current is only 19.2 amps. That's too low to blow either fuse. So even though there's a phase-neutral transposition, the supply stays live, making it unsafe. Always test polarity before turning power on. Reverse polarity in multi-phase or three-phase installations introduces severe operational and safety issues. Correct phase rotation is essential to prevent damage and maintain safety. Confirming phase rotation involves specific tests to ensure accuracy and safety. These tests protect equipment integrity and personnel from harm. Excellent work. Understanding polarity and phase rotation ensures electrical safety. Now, let's reinforce these concepts with some Moodle questions. Hi everyone, I'm Whitroy. In this short lesson, we're focusing on general arrangements and specifications, especially how to select and apply protection devices that keep installations safe from overcurrent, short circuits, and voltage irregularities. Protective devices like MCBs, RCDs, AFDDs, and fuses must automatically disconnect the supply under overload, short circuit, earth leakage, or arcing faults. AS/NZS 3000 Section 2 outlines the minimum requirements for these essential safety functions.
To choose protection devices correctly, use the tables in Appendix C of AS/NZS 3000. These match conductor sizes to suitable device ratings under various conditions for both single-phase and three-phase systems. Rated current is the maximum load a device can carry continuously. Excess current protection ensures the device interrupts the supply when current exceeds that limit, helping to prevent damage or fire.
Each term defines a critical performance limit of protective devices. The correct understanding helps ensure safe device selection, especially for sub-circuit protection. When working with photovoltaic or DC systems, use DC-rated protection devices. They handle continuous DC arcs and often have higher braking capacities than their AC counterparts. Excellent work. Let's apply what you've learned now with some practice Moodle questions to sharpen your decision-making when selecting protection devices. Hi everyone, I'm Whitroy. In this short lesson, we're talking about undervoltage protection, what problems it causes in installations, and how to choose the right protective devices to prevent damage and instability. Too much voltage drop in an installation can cause lights to flicker, motors to overheat, and appliances to fail. It also leads to serious risks in minor circuits, especially where long cable runs are used. Managing this is part of good electrical design.
When selecting protection for low voltage situations, look for devices designed to disconnect circuits during undervoltage conditions and reconnect safely once stable. Think about how fast they act, how they reset, and if they match the system's requirements.
Awesome work. That's our overview of undervoltage protection. Let's now dive into some Moodle questions to test how to assess volt drop issues and choose the right solutions. Hi everyone, I'm Whitroy. In this short lesson, we'll explore RCDs, how they work, where they're used, and what standards guide their selection and installation. RCDs work by monitoring current flow and disconnecting the supply when leakage is detected. This helps protect users from electric shock and can prevent fires caused by current escaping to earth.
According to ESR 24, an RCD that doesn't trip within the required current or time is deemed unsafe. This is why testing and compliance are essential in all installations.
There are different types of RCDs for different needs. Type A is standard, Type B is for EV chargers, and Type S is fire rated. Medical areas must use Type 1 10 mA RCDs, not Type A, and 10 mA RCDs are needed in child accessible areas. Type S RCDs are time-delayed devices that trip at 100 or 300 milliamp to reduce fire risk from persistent leakage currents. Installed at main switchboards, they work with downstream 30 milliamp RCDs to provide selectivity and protect property from faults like smoldering insulation. Installation of RCDs varies across settings. Whether it's a home, office, or factory, the correct RCD type must be selected and placed according to AS/NZS 3000. This applies to new builds, additions, and retrofits. Nice work. That's 10.6.3 on RCDs. Let's now test your understanding with some Moodle questions covering types, tripping thresholds, and correct applications. Hi everyone, I'm Whit Roy. In this short lesson, we're focusing on arc fault detection devices, or AFDDs, how they work, the risks of arc faults, and why these devices are valuable in protecting final subcircuits from electrical fires. Arc faults are dangerous and often caused by damaged cables or poor terminal connections. Series arcs happen within a single conductor, while parallel arcs occur between conductors. Standard protection like RCDs or MCBs may miss these faults. This is where AFDDs come in.
AFDDs use advanced electronics to monitor current flow. They identify abnormal arcs based on waveform and noise, and disconnect power before a fire can ignite. They're especially helpful in detecting faults that traditional devices can't catch.
Nice work. That wraps up lesson 10.6.4 on arc fault protection. Let's head into Moodle and test your understanding of AFDD operation, risks, and how they work to prevent electrical fires. Hi everyone, I'm Whit Roy. In this short lesson, we're looking at isolating transformers, what they do, why they improve safety, and how they're used with appliances, especially in special environments. An isolating transformer separates the supply from the appliance, eliminating a path for shock current through earth. It provides maximum safety when only one appliance is used. There's no fault return path.
If multiple appliances are connected to one isolating transformer, their earth continuity conductors must be bonded together, but must not be earthed. This keeps all exposed conductive parts at the same potential while maintaining isolation.
Isolating transformers are often used with handheld tools or appliances in hazardous conditions. They're not always enough on their own, but combined with other protections, they significantly reduce the risk of electric shock. Nice work. That wraps up 10.6.5 on isolating transformers. Let's now move into Moodle and explore when and how to apply them safely. Hi everyone, I'm Whit Roy. In this short lesson, we're looking at cabling systems, how to select the right cable for different situations, what factors must be considered, and how to apply the correct tables from AS/NZS 3000 and AS/NZS 3008. When choosing a cable, you must consider the load current, voltage rating, installation environment, run length, mechanical strength, and any derating factors. Short circuit current levels and earthing requirements are also key. This ensures safety and reliability.
To assess a cable for a job, combine all the above factors. For example, a long run in a hot ceiling space may need a larger cable to handle voltage drop and heat derating. Always think about how the actual job site affects the cable's performance.
When selecting mains and submains, refer to AS/NZS 3008 1.2. Tables like 13 and 24 help choose cable size based on current carrying capacity, ambient temperature, and installation type. Correct selection avoids overheating and meets safety standards. For subcircuits, use AS/NZS 3000 to select cable size. Match the load current and installation method to the table values. This ensures the cable won't overheat or cause voltage drop problems. Nice work. You now know what factors to assess and how to apply the correct tables from the standards to selecting the right cables. Let's practice with some Moodle questions next to check your skills. Hi everyone, I'm Whit Roy. In this short lesson, we'll look at how to determine maximum demand for different installations, why it matters, the methods involved, and how to apply the correct sections from AS/NZS 3000. Maximum demand is the calculated worst-case current a circuit may draw. It's not a straight sum of everything connected. We apply diversity factors from AS/NZS 3000 to reflect how loads behave in real life.
For houses, use Appendix C Table C1 to find demand values for each load type. For example, multiple socket outlets are calculated with decreasing amperes by points. This ensures cables and fuses are right-sized for realistic use.
In non-domestic sites, maximum demand includes motors, groups of lighting circuits, and three-phase loads. You still apply demand factors, but check the right rows in Appendix C. This helps you calculate total installation loading for switchboards and feeders. Great work! That wraps up maximum demand under 10.7.2. Whether for a home or a factory, knowing how to calculate it keeps your system safe and efficient. Let's now try some Moodle questions to practice. Hi everyone, I'm Whit Roy. In this short lesson, we'll look at voltage drop, where it happens, what affects it, how to calculate it, and how to choose the right cable to keep it within limits. Voltage drop occurs when cables are too long, too thin, or overloaded. It causes lights to dim and equipment to underperform and can even damage motors. AS/NZS 3000 sets limits to keep equipment working safely.
The more current you draw, the more voltage you lose across the cable. A bigger load or a longer run will increase the drop. That's why load size must always be considered in voltage drop calculations.
To calculate voltage drop using the VC method, multiply the current by the length of the run and the VC value from AS/NZS 3008, 1.2, table 42 or 45. Divide the result by 1000 to get volts. VC is the voltage drop per amp per meter. Always make sure the final result is below the maximum limit, which is usually 5%. To reduce voltage drop, you may need to upsize the cable. Always balance the load, length, and conditions when choosing a conductor, and double check with AS/NZS 3008 to stay compliant. Great work! That wraps up voltage drop under 10.7.3. You now know how to recognize, calculate, and control voltage drop in your designs. Let's jump into some Moodle questions next. Hi everyone, I'm Whit Roy. This lesson is about testing competency, using the correct instruments, following the right procedures, and understanding test results. All practices come from AS/NZS 3017, 2022. Before testing any installation, make sure you're using the correct instruments. AS/NZS 3017 lists the essential tools for verification: continuity testers, insulation testers, voltage indicators, RCD testers, and more. Each test has a purpose, and the right tool ensures reliable results.
Use Cat 3 instruments for submains and Cat 4 for mains testing. Your test gear must be suitable for the site environment, especially in damp or hazardous areas. The instrument's function, range, and safety rating must match the job. Use a dual contact voltage indicator to confirm isolation. For low resistance testing, use a low range ohm meter that can measure small values accurately with 2 decimal places, within 5% error. Before any testing, conduct a visual inspection to check for hazards such as damaged cables, incorrect terminations, or exposed conductors. Use the checklist in Section 3 to ensure safety and compliance. AS/NZS 3017 sets out a specific test sequence to follow. Always start by testing that the installation is de-energized, then test earthing continuity, insulation resistance, polarity, earth fault loop, and RCDs in that order to avoid invalid results. Use a continuity tester to confirm the main earthing conductor has low resistance. Then test insulation with 500 volts DC. The result must be at least 1 megaohm between conductors and earth. Polarity testing ensures actives are correctly switched and fused, and that neutrals are not switched. Clause 4.6 outlines the correct methods and required outcomes. Verify polarity at all accessible points, including socket outlets. In 3-phase installations, use a phase rotation tester to verify correct sequence. Incorrect phase order can cause motors to run in reverse or not at all. Always test outlets before energizing connected equipment. Measure loop impedance at the furthest outlet. The Z's value must allow the protective device to operate quickly in a fault. Use device curves or table 4.5 to verify compliance. Use the test button or an RCD tester to confirm the RCD operates correctly. AS/NZS 3017 requires functional testing only, not measuring trip time. Always check polarity before using an independent earth probe. Test earth electrode resistance using the fall of potential or clamp meter methods. Values between 50 and 200 ohms are expected in good soil. Care is required to prevent elevated touch voltages during this test. To ensure touch voltages are within safe limits, simulate body resistance using a 2kΩ resistor and measure across exposed conductive parts. Ensure readings fall within values allowed in AS/NZS 3000. Neutral integrity is verified using impedance, voltage, or current methods. Under load, clamp current in actives and neutral should match. Voltage between neutral and earth must be under 6V. Testing must be done in the right order, with the right tools, and interpreted correctly. These checks confirm the safety of your installation, so let's practice what we've learned with some Moodle questions. Hi everyone, I'm Whit Roy. This short lesson focuses on why ongoing professional development matters for electrical inspectors, not just for licensing, but for leadership, safety, and industry guidance. To renew your EWRB inspector license, you need to complete an approved refresher course. This helps you stay up to date with changes in AS/NZS 3000, ESR 2010, and safe work practices. Your license must be renewed every 2 years. Don't leave it too late. As an inspector, others may come to you for advice. Whether you're mentoring apprentices or supporting your team, you need to give clear, up-to-date information. The industry relies on you for leadership and safety, so keep learning and sharing. Professional development isn't optional, it's essential. Stay current, do your refresher, and stay familiar with evolving regulations and standards. Now let's go through some Moodle questions to test your understanding.